of the navigation message is that you would get the signal, and with the help of these telemetry and handover word kind of information, you can get the information about which signal, which satellite signal you have to uh, access, and the synchronization pattern which facilitate the access to navigation data. Further, in handover word, uh, you will use this so-called the access to the segment of the P code, weak segment of the P code, where you have to perform certain correlation mechanism. So that is somehow we'll be discussing today how this correlation phenomena is occurring. But for that time being, this handover word is helping us to shift from CA code to P code, and exactly at the segment where we need to open up the correlation. So, and this content of subframe, we have explained that it is 5 subframe, and we have explained this in the previous class. So in general, you just understand that GPS clock and ephemeris parameter. What are those ephemeris parameters that are available? So I'll be giving much more time on this slide because it needs little more introduction from your end also. I'm just opening the recording. Okay, recording is started. Thank you. So the time parameter. See, there are, everything is related with the GPS satellite time. Okay. So time parameter, one is TOE. Then there is a TOC. Then A0, A1, A2. So first let us discuss about the time parameter. So whenever you are preparing any message or information for the users, what you need to do? You need to stamp with the time in parameters. So reference time for ephemeris parameters, reference time for clock parameters. Okay. And these two time represents that at what epoch your information is created. So TOE says, just a moment. Okay, so this TOE and TOC represents the reference time for ephemeris parameter and reference time for clock parameter. So what is happening? Let us just understand this fact that whenever you are preparing certain information for the users, you need to also make it a stamp at the same time. So just like every page is a time stamp, every page is time stamp. So the whole set of information which is being transmitted, we need to tell the user that at what time it is being prepared. Okay. The TOC says reference time for clock parameters. As I've told you, although at the satellite end, it is the atomic clocks which are being there. But frankly speaking, these clocks gets affected by lots of forces that are acting over the satellite. And these satellite clock gets little drifted towards certain, or the offset which is being created is because of these forces. So when you prepare the clock parameter data, you also stamp it that this time these parameters are created. What are those parameters? Polynomial coefficient for satellite clock correction, that is representing the bias, drift and drift rate. Okay, then you have a IOD, issue of data. Okay, this whole navigation data will have a IOD stamping also, that is at this time, at this date, it is issued uh, kind of. Please remember, this time parameter is important because satellite, let's say, have transmitted the signal, or this satellite is transmitting the signal at certain time, but you are receiving at a different time. So in that meantime, satellite will be at a different position. And in that meantime, you would also be knowing that what type of forces that are acting over it. So orbital parameters includes semi-major axis, eccentricity, inclination, longitude of the ascending node, argument of perigee, mean anomaly. Now, can anyone explain or give a guess that instead of writing major axis, they are writing square root of the major axis? Why? Just think. Any guesses? So the square root is just used to save the space. If information of semi-major axis, which is very large, if it is written, then it would need a lot more space requirement. So square root of a would be taking less space. That's why they are using square root a. So eccentricity, these are the orbital parameters. Perigee is the point. The perigee means the point where the satellite is at the shortest distance with respect to Earth. Okay. And then mean anomaly, that is position of the satellite in the orbit at TOE, which is so-called reference time for ephemeris parameter. Please remember, these all orbital parameters or ephemeris parameters are stamped at TOE. Then you have orbital perturbation parameter, which is delta n, that is mean motion difference from computed value. Capital phi dot, which is rate of change of right ascension. I dot, there is a I naught, and then I'll say I naught dot. Instead of saying I dot dot, I'll say I naught dot. So I naught dot says rate of change of inclination. CUS and CUC says amplitude of the sine and cosine harmonic correction term to the argument of latitude. CIS and CIC is the amplitude of the sine and cosine harmonic correction term to the inclination angle. CRS and CIS is the CRC is the amplitude of the sine and cosine harmonic correction term to the orbital radius. Now just understand this, the orbital perturbation parameter. Imagine you have Earth, imagine you have an orbit. Just imagine you Earth, the orbit. Now, if you consider that orbital plane is of wire, let's say for the time being, it is a very stiff wire, and you place a force and you just exert the force, what will happen? It will vibrate, isn't it? Vibration will occur. This vibration will result in change in inclination also, change in the radius also, as well as change in the argument of the latitude also. Clear? Why? Because forces is not over from top to bottom, bottom to top also, and at the terms of elongated also. You can just uh, oh, provide some tension in the outward direction. You can just pull it off. What will happen? In any three cases, force can be acting over in any kind of direction. So in any cases, what will happen? There would be some kind of harmonic motion or periodic motion for a period of time. So that's why we are considering these amplitude of sine, cosine, harmonic correction term. The orbital perturbation parameters, they are nothing but the rate of change of right ascension, because as you could also understand that Earth is moving at the same time orbits, the position of right ascension would also be changing. So rate of change would also be marked. Inclination is also varying with respect to time in the space. That would also be needed to compute the rate of change of inclination. So these time parameter, satellite orbit parameters, orbital perturbation parameters, these are all terms which are there in your navigation message. So when we conduct the laboratory on navigation message for satellite coordinate computation, you all will use these parameters one by one. So there is no need to worry. Just at this time, let us just understand this whole concept of the importance of the navigation message. What is the importance of the navigation message? So navigation message helps us in trying to identify the satellite position at a certain epoch. At the same time, we also need to see what is the health status of the satellite. So at this particular slide, we are only focusing towards the computation parameter for the satellite position. But at the same time, the health status and everything are also explained during navigation message. So any question at this point?
Sir, how taking root of semi-major axle will reduce the memory?
आगे जरा आइए बेटा एक जो स्पेस एलोकेटेड होता है नेविगेशन मैसेज में उसको एक सर्टेन स्पेस एलोकेट किया जाता है सपोज वो 2 बिट इंफॉर्मेशन का होगा 8 बिट इंफॉर्मेशन का होगा है ना जैसे आप लोग इमेजरी में देखते हैं कि 0 to 255 या -125 टू +125 आप देखते हैं ना इस तरीके से तो उसी तरीके से इसमें भी इंडिविजुअल वैल्यूज को या इंडिविजुअल इंफॉर्मेशन को एक स्पेस एलोकेट किया गया कि 0 से 1023 वाली ही इंफॉर्मेशन आपकी रहेगी उसके अंदर तो वही स्क्वायर रूट का करने का मतलब है कि इफ समथिंग यू हैव टू राइट 100 एंड इफ यू टेक ए स्क्वायर रूट यू कैन कम्युनिकेट 10. So people at our end, we as a user, we know that we do not have to use the square root. Instead, we have to use the complete A. So we just need to make a square of it.
Okay, sir. But suppose there is a decimal digit number, like 9, something 9 point something. If you take the root, we get some number. Now, if you want the main value, and if you square root, we maybe will not get the exact data.
Yes, exact. Yeah, here we are not in. I mean, when we do this, we are taking consideration of the certain decimal places. But yes, you are very right that whenever we take the square of it, we may not use it perfectly. That's true. But at this end, the requirement, the effect of the saving the space is much more than providing the accurate or exact value because we do not know the exact value. It is only being updated regularly. So it is considered that the value which is being used for A will not be changed in next 18 hours or so or 8 hours or so until the next upload by the control segment because these parameters, the satellite orbital parameter, the perturbation forces, they are all being given as a predicted value by the control segment. Satellite end would only be there for time stamping, that these are the time stamping at what time I'm dispatching at user end. This is it. So time stamping is a critical parameter which is very much precisely known. That's why they're at that satellite, and we have the so-called atomic clocks.
Okay, sir. Thank you.
Any more questions? So, did you get this proper understanding of the requirement from the navigation message? Any questions? Can we move ahead? जरा आप इसको एक बार देखिए सभी लोग. कोई डाउट इसमें, किसी को कुछ ना समझ में आ रहा हो? Okay. So why this signal is complicated? Let us focus on this. Why it is complicated? Because it is a multi-user system and there is only one way measurement, that is a listen only system. You cannot communicate anything to satellite. You just use the data. Then real-time positioning, that means simultaneous measurement to many satellites need to identify different signals. Unambiguous range measurement need to determine signal delay, satellite position needed, broadcast ephemerides. So real-time positioning means we have to simultaneously have measurements from many satellites. We need to identify the different signal that is coming from different satellites. So from this initial end, it looks as a complicated, but in fact it is very streamlined. Otherwise, if it is a really complicated, then there would be no user at all, isn't it? Or a very limited user. But we have huge users of GPS. Without knowing your father or mother, they are also using it. Okay, so understanding the mechanics of a particular technology is a different thing, but using is a different thing. So frankly speaking, the GPS is a user friendly technology. Okay, high accuracy positioning, that means high frequency modulation, P code at 10 megahertz, dual frequency to avoid ionospheric delay, microwave carrier frequency from 1.2 to 1.6 gigahertz, anti-jamming requirement, spread spectrum technique. So these are all requirements that says that your this system or the signal is complicated, but in fact it is very streamlined. Okay. Okay, coming back to this principle of position fixing, there are two types of positioning that we do. One is basic principle of position fixing, is that of the resection in the surveying that we do. Okay, so space resection here we attempt in the case of GPS. The two types of positioning fixing are used. One is positioning by pseudo ranging. Second is positioning by carrier phase measurements. Okay, so one, we do the positions by pseudo ranging, and second, we do the positioning by carrier phase measurements. Okay, let us see individually. In the case of code based positioning, so let's say I just want to recall that what we have done, we have seen that the signal is traveling from space to uh, user, and that signal, carrier signal, is modulated with the codes. That codes, when you use it, they are called as code based positioning. That is also known as pseudo ranging, because you are using the time travel of these codes and multiplying by the speed of light, and you are estimating the pseudo ranging. So pseudo range is a measurement of distance between satellite and receiver antenna, referring to the epoch of emission and transmission of code. अब आप देखिए TOE मतलब इस समय टाइम ऑफ ट्रांसमिशन, ये स्टैम्प्ड है वहां पे, आपको पता है कि टीओटी पे सिग्नल निकला हुआ है और किस समय रिसीव हुआ ये भी आपको पता है, बट यू नो दैट देयर आर एरर्स, बट फ्रॉम सैटेलाइट एंड यू कैन करेक्ट फॉर इट. So t plus delta t at satellite end can be corrected, or a corrected value can be given, but t plus delta t of the receiver, you can use it as a unknown. So pseudo range is a measure of distance between satellite and receiver antenna, referring to the epoch of emission and reception of the codes. Okay. Transmission time is measured by correlating identical PRN codes generated by the satellite with those generated internally by the receiver. That means transmission time is measured by correlating the two. What is two? identical PRN codes generated by the satellite with those generated internally by the receiver. So there are things how there are two codes. One is what satellite is transmitting, and another is what receiver is generated in itself in inside it. So these are nothing but the CA code that they are generating for correlating phenomena. Okay, so various errors such as satellite and receiver clock offset, atmospheric delay, multipath tend to corrupt the true range. That's why this measurement is called as pseudo range, because they are already corrupted. Okay, then clock offset can be computed so that the relative time of transmission and reception of radio signal is known. Just have a look. Okay, so this is the code based positioning. Let us see the example. So this particular is the satellite CA code, -1 +1 -1 +1 -1 +1 and so on. You can see that. Okay, once the satellite receiver receive the signal, since as I told you, the authorized receiver knows that which signal the so-called which satellite signal is coming to them in terms of CA code, because they are authorized receiver. So what they do, they generate the internal replica of the similar code and they try to make shift in the time domain to get a perfect correlation. So let's say in at this present distance, let's say 10 position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10 binary chips were correlated and they found that it is positive 0.40. So that means it is not perfectly correlated. So they are again being time shifted to each other to get a perfect correlation of the 1, where individual chips are multiplied. -1 multiplied by -1 would become 1, +1 multiplied with +1 would become 1, and so on. After then multiplied by all 10 chips divided by 10, they get perfect 1. So the moment they are time shifted in the time domain, this time shift required for correlation is considered as the time of travel that this chip would take to reach the receiver end. So the distance to the satellite is measured using code sent from the satellite. Same code which is generated simultaneously in the receiver. Travel time of the signal can be measured from this correlation and the distance calculated using the value of or a speed of light. with the known velocity of radio wave and by precisely measurement of the time of travel, this d is equal to c cross dt. Okay, so with this delta t is known, you can multiply it with the speed of light and you can get this pseudo range. A similar figure of the peak is available at the bottom, where you see the correlation peak is available of 1 at this delta t epoch. Apart from else places, it is less than 1. Okay, just take a look. So, I mean, strictly speaking, the pseudo range observable is based on a time shift. We can also explain this similar concept by just saying that whenever you talk on a telephone, let's say, this time lag with the previous telephone was a fraction of second. I mean, the moment you say, somebody at the other end listen it, but still there was a certain lag. We could not identify it, but there is some lag. That lag is actually being identified here as a delay in the travel time or propagation delay. That means satellite has transmitted at certain time t1, but you received at t0. So this t0 minus t1 has to be identified by some mechanism. That mechanism has been chosen by GPS technologists as a code correlation. Okay, in that code correlation, they generally generate a replica of 10 chip segment. Okay, 10 chip segment, and they generate and they try to make it shift in the time domain to get this perfect correlation of 1. When they get it, they say that this is the time shift that we have taken to generate the perfect correlation. So in GPS, the elapsed time is known as the propagation delay, and it is used to measure the range. The measurement is accomplished by the combination of the code. Okay. So this code correlation process, you can You can time shifting. You are shifting the codes in the time domain to get the perfect replica, to get the perfect correlation. I'm sorry. So this autocorrelation phenomena, which we are talking here in this slide, says that almanac information from the navigation message of the first satellite a GPS receiver acquires tells it in which satellite can be expected to come into the view. So with this information that okay, these satellite numbers are expected, the receiver can load up the pieces of the CA codes for each of those satellites. Then the receiver tries to line up the replica of CA code with the signal it is actually receiving from the satellite. Okay, so actually lining up the codes from the satellite with the replica in the GPS receiver, this process, lining up the two replica of the GPS codes with the actual one which is coming from the satellite, is called as autocorrelation. And the function of these code states, which we are using as 1 minus 1 1 minus 1, they are, I mean, in electronics term, they are transmitted into a loop. So we are tracking loop. So if a tracking loop of code states generated in a receiver does not match code states received from the signal, so how does the receiver know? You know that. So in that case, for example, the sum of the products of each of the receiver's 10 code states with each of the code states from the satellite, they multiplied it and sum it and then divide by 10. Okay. So this perfect correlation will only be happening when you shift the replica code in time domain. I hope you are getting the essence of this code correlation. Any questions? If you have any basic doubt, there's no problem. You can ask. Any questions? चलिए इसको देखिए, कोड बेस्ड पोजिशनिंग कैसे हम लोग लिख रहे हैं। क्वेश्चंस जरा देखिए, इसमें भी जो बहुत सिंपल कॉन्सेप्ट लिखा हुआ है. In code based positioning, 4 unknowns are identified, 3 position and receiver clock error dt. 4 equation will be required, and this is one sample equation. अब कैरियर फेज पोजिशनिंग देखिए. As I've told you, not only the replica, not only the codes which are being modulated over the satellite carrier signal, it is the carriers also can be used based on their properties for positioning purpose. So first example is explained with the help of EDM, which is electronic distance measurement concept, where from EDM the signal is transmitted, it is gets reflected by some reflector, and we know the T1 and T2. That means the transmission and reception. We can use it by making use of this T1 minus T2 multiplied by C, which is equal to twice the distance which is there between prism and the EDMI and the reflector, because signal has gone to the reflector and reflected back. So this becomes 2D. One direction going, another is transmitted back. So this 2D is equal to m lambda plus delta lambda. M lambda means number of full cycles the signal has covered, plus delta lambda, that is the phase difference. After reflecting back, the phase difference it has observed at receiving end. So the similar approach is used in EDM, active ranging system, modified approach in the passive ranging used in GPS measurement. So in GPS, it is the difference between the received satellite carrier phase as sensed by the receiver antenna and the phase of the internal receiver oscillator. One thing I want to tell you that you should focus that since it is a one-way system, user doesn't have to communicate with the satellite. It is only receiving the carrier signal. Okay, it is only receiving the signal from the satellite. It has to do lot of process inside the receiver. In code also, code-based positioning also, we have seen that the code correlation phenomena is working to get the time of travel estimation. Okay. And at the and second is that the so-called carrier phase positioning, it is the difference of the phase, which is the phase difference which is being observed of the satellite carrier phase, which is being received at the receiver antenna at the phase of the internal receiver oscillator. Okay. So let's say this is your satellite at T naught. This is very good example. Just focus it here. This is your satellite T naught. It is transmitting the signal, continuous signal. Okay. And this is T1. At the same satellite is transmitting the signal, isn't it? The continuous lock, which is being there. Once satellite is locked with this receiver, it is moving in this orbit and at the same time transmitting the signal. That's why we get the data at every epoch, isn't it? Because it is continuously locked. It is not like that कि आपने satellite एक समय डेटा दिया फिर बंद हो गई, फिर दूसरा दिया फिर बंद हो गई ना. सैटेलाइट एक बार लॉक हुई आपके रिसीवर के साथ तो वो कॉन्टिन्यूअस तब तक टच में रहेगी जब तक आप अपना रिसीवर बंद नहीं करेंगे. ओके. So this ambiguity, so in carrier phase measurement, receiver measures the fraction of one wavelength when it is first locks onto a satellite and continuously measures the carrier phase from that time. तो आप ऐसे समझ लीजिए कि आप एक बुलक कार्ट है, आपके गेट के सामने से निकली, आप उस पर चढ़ गए. Now that bullock cart is moving from one point to another point. It is moving. तो जब आप बुलक कार्ट पे पर चढ़े तो आपने देख लिया कि पहिए में एक रेड निशान है. आप उस रेड निशान को फॉलो कर रहे हैं, 1 2 3, तो उसके पूरे फुल सर्किल मूवमेंट को आप ऑब्जर्व कर रहे हैं और लेट्स से आप एक उसके डेस्टिनेशन तक पहुंच गए. तो जब आप डेस्टिनेशन पे पहुंचे तो आप कहेंगे कि इसने 50 राउंड ऑफ फुल सर्किल किए प्लस आज अभी प्रेजेंट स्टेट में जब ये रुका हुआ है ये 1/4 ऑफ इट्स फुल सर्किल. That means that 50 round it has completed. So you will say 50 multiplied by 2 pi r plus 1/4 of the lambda, which is the 1/4 of the whole circle which is there at present, multiplied by that fraction length. So when you multiply the 2 pi r by 1/4, you will get the complete distance traveled from the moment you onboard the bullock cart till the time it has ended. Similar concept is being used here. So in carrier phase measurement, receiver measures the fraction of one wavelength when it first locks onto a satellite. भाई जब शुरू में सिग्नल मिलेगा तो सीधे फुल सर्किल थोड़ा मिलेगा. वो जो सिग्नल आया वो उसके एंटीना पे टकराया, उसने फेस मेजर कर लिया कि फ्रैक्शन ऑफ वेवलेंथ क्या है. फुल सर्किल फुल कैरियर ये होता है. इट इज नॉट स्टार्टिंग at 0, it is starting at 30 degree phase different, 40 degree, 45 degree, and so on. So receiver measures the fraction of one wavelength when it first locks onto a satellite and continuously measures the carrier phase from that time. The number of cycles between the satellite and receiver at initial startup. The number of cycles between the satellite and receiver at initial startup known as integer ambiguity और इनिशियल साइकिल. मतलब जिस वक्त आप बुलक कार्ट पे बैठे उसके बाद का तो आपको सब पता होगा, लेकिन बुलक कार्ट कहां से चल रही है, कहां तक आई है, आपको कुछ नहीं पता. सो आपने स्विच ऑन किया रिसीवर, तो स्विच ऑन करना और लॉक होने के पहले सैटेलाइट के सिग्नल ने कितना पाथ ट्रेवल कर लिया था, आपको उसका कुछ भी आइडिया नहीं है. वो एम्बिग्यूटी रहेगी, आपको एस्टिमेट करनी पड़ेगी. So the number of cycles between the satellite and receiver at initial startup known as integer ambiguity or initial cycle and the measured carrier phase together represent the satellite carrier satellite receiver range. And ambiguity क्या होती है? Initial ambiguity value must be determined for carrier phase measurement processing. It remains fixed after initial lock. Ambiguity resolution, the process of finding out the unknown integer number of cycles is known as ambiguity resolution. Cycle slip, it is the change in the ambiguity value because of certain hindrance. That means your receiver got switched off, let's say for timing. The moment you again switch on, there would be a new ambiguity value. So it is a concept just like the moment you switch on the receiver, satellite signal is already in somewhere in between you and the satellite end, and you locked with the signal, but the signal has already traveled certain distance. You do not know how much it has traveled, so you consider that unknown region as ambiguity. You include it as an observable. or include as an unknown in your equation, but your objective is to estimate that n also. But because if you get too many observation, you can estimate it very quickly. So the ambiguity value that remains fixed over the time since the lock was established, you can write this equation. You can focus on this equation and read the content for time being. Any doubt? Second, this equation which is we are writing, we can explain it in a bigger manner. Let's see. You have this satellite as T1. Sumit, आवाज आ रही? Hello.
Yes, sir.
Yes, there is.
So this satellite which is at T1, it has transmitted the signal. It is continuously logged. So phase change, which was there as delta phi 1, delta phi 2, delta phi 3, which will change because there is no point in that changing in the phase difference, because it will change because satellite is moving somewhere away from you over the period of time. So distance will change as well as correspondingly delta phi will change. But you could see if it is a continuous lock is maintained, the initial ambiguity will not change. It is same. This is a very important concept, but your so-called student may not get this completely. See, GPS orbit is there. You have a satellite at T1. Your receiver is connected. Initial phase difference is observed plus the ambiguity. So this point says that this time, let's say satellite has locked with the receiver. So this time you have observed delta phi 1 plus n t naught, but at over a period of time, this delta phi 2 will change, delta phi 2, delta phi 3, but the ambiguity will remain same. It will only change if your receiver is switched off or lock is lost. So how the phase difference, the phi ti you will write? You will write phi ti as fractional phase at t1 or ti plus integer full cycle since t naught plus ambiguity at t naught. मतलब जब यहां से आप मेजरमेंट ये करेंगे तो यहां पर भी कुल फुल साइकिल कंप्लीट हो गई होंगी. At this point also some full cycle would have been completed. Here also some full cycle have been completed, just like the bullock cart case. You have onboarded the bullock cart at this point. From this point till the satellite is in your position, you can count all number of full cycle plus fractional phase. But ambiguity, that means from where the bullock cart has started, you do not know. You have to estimate it. Similarly, here you can write the phi ti is equal to fractional of phi ti plus integer phi t naught ti plus n t naught. That means integer number of cycle that has completed between since t naught to ti, you know it, fractional which is at ti plus ambiguity which is at t naught. So this equation is written like that. Just look at this equation. So this figure explains. I hope there is no problem in this figure. I hope you get this sense of the phase measurement. Any questions? Any questions? Okay, so point positioning is the next concept which I want you to focus. It's very, because these are the points where you will start using the receiver. If you do not know the internal mechanics, not know the working, do not want to work in the internal mechanics of the receiver or functioning, then you simply use the data set. So when we use it in certain ways. One is point positioning. A single GPS unit located on an unknown point is used to determine the 3D coordinates of that unknown point referenced. Okay. Accuracy of such method depends on the duration of observation and accuracy of satellite ephemeris. Okay. So a single GPS unit located on an unknown point is used to determine the 3D coordinates of the unknown point referenced. Okay. Accuracy of such method depends on the duration of observation and the accuracy of satellite ephemeris. Okay. How long you collect the data and how well you know the satellite coordinates. Second point is saying how long you collect the data and how accurate your satellite coordinates are. Second is opposite of point is relative positioning or differential positioning. When two or more GPS receivers receive signal from the same set of satellites simultaneously, one GPS unit known as reference or base station is always positioned at a known point. आप एक रिसीवर को एक known point पे छोड़ करके रख देते हैं लंबे समय के लिए. The observation are processed with respect to base station and it will cancel out the common error between base and rover because they are observing the same pairs of the satellite. So accuracy achieved is much higher than that in point positioning because errors common to both receivers gets cancelled. These methods are broadly grouped as follows. One is static point positioning, where all receiver remains stationary and collect carrier phase over a period of time. Then the kinematic positioning, one receiver remains stationary at reference station while other moves from one point to another. Name suggests their approach in data collection. Static means you will static at a same point. Kinematic means you will move. But in the context of relative or differential positioning, one base station will always be there. So one base station will be fixed. It will not move. It will be there at its position. But if you are working in static positioning, you will stay at one place. You do not move. And if you are working in a kinematic positioning, you will move or change place. This is a figure of relative positioning. Just closely observe. So let's say in a building, you on top you have made the base station, and at the top the base station, which is observing the same pair of satellite. You could see here, this is the same pair of satellite which has been observed by the base station as well as the receiver station. And this DGPS concept says where you can achieve positioning accuracy of 1 meter or so based on same satellite constellation code phase as well as pseudo ranges, then radio link by which you can transmit the correction. How you can transmit the correction? You can transmit the corrections through radio modem, or as well as the network services, you can also take care of that. So this is the concept of DGPS. DGPS says you have a base station, you have a rover station, and if you are working with code pseudo ranges, then this terminology is known as differential GPS. If you are working with carrier phases, this terminology will be known as relative positioning. The difference between these two are very simple. The differential GPS is popularly used for code pseudo ranges. When you are observing the code pseudo ranges and you are using this base and rover concept, this is called as DGPS. But when you are using the carrier phase measurement and you are using base and rover receiver, that positioning is known as relative positioning. Just observe this figure very carefully. Any questions on this figure? Chaliye. Let us discuss certain applications. So, as we all know that GPS is one of the fastest moving technologies in the world. It had find application in almost all areas requiring spatial coordinate or time. The following is the list for major areas. One is utility industry, natural resources, precision farming, civil engineering applications, structural deformation, open pit mining, land and marine seismic surveying, airborne mapping, sea floor mapping, vehicle navigation, transit system, retail industry, cadastral surveying, stakeout. They're all endless. I mean, by the name itself, you can understand what we are doing. In utility industry, you do the asset management kind of thing. Natural resources also, you do the asset management kind of thing. Precision farming, where in close integration of the multi sensor, you do the precision farming. Without GPS it is not possible. Even every technique for satellite image processing, you need the GPS coordinate. For lidar, you need the GPS coordinate. Without GPS, no technique is possible at present era. It is not possible. You do you for UAV mapping, you need GPS. For all possible kind of application, you need understanding of the GPS. Land and marine seismic surveying, you need GPS. Airborne mapping, you need GPS. Seafloor mapping, you need GPS. So for all kind of application, you need the input from the GPS technology. So with this, we stop here. I have a quiz, arranged a quiz for you. You can will next class we will discuss about the GPS receivers. The quiz will start at 4:35. You just take a 5-minute break and quickly reassemble. Okay, for attempting the quiz. I'm just going to assign it. It's very simple and quiz, but do not copy. I mean, don't cheat. Just simply try to attempt it from your